Okay, this is a fourth problem, which is an optional, but I want to provide the solution to you. And this is about the bonding in metal complexes. And here they give the contrasting two examples, which is a metal ion, which is Fe, is coordinated by water, 3 aqua, or 3 cyano. And if you're looking at the periodic table, Fe, their atomic number, Fe is 26. Okay, that's an atomic number. And it has the same configuration, electron configuration is an argon is a closest noble gas. And then you have a 3D, 6, and then you have a 4s2. Okay, so that's the one that they have. And then what we are dealing with here, if you can see, this is a neutral, so we are talking about Fe3+. And so does here, if you look at here, FeC and cyano, which is a -6, and total charge is -3, so therefore we are talking about identical Fe3+. So Fe3+ is an argon with 3d5. So you have a 5 d orbital electrons by losing 3 electrons from the neutral Fe, and then how those electrons will be located in the energy diagram. So you have to understand the d orbitals. So d orbital is what is known for the inorganic chemistry. So this is a d orbital. There are 5 d orbitals, and I kind of show the one that is shown up here in the energy diagram. So this d orbital was degenerate at the 5 d orbitals, and then they are going to be split up, what they call the octahedral split, when they are coordinated by these neighbors. So, and then they are the one that there's a Z2 and X2 minus Y2. This is what I call they are in the axial and in the position, and these are the one in the sort of the somewhere in between axial, like in between the axial position, like 45 degrees. So let me show the pictures of what the Z orbital means. Right. So Z orbital, as you can see, they are kind of an axial, and the x minus 2 is along the x-axis and the y-axis. So geometrically, so they occupy all x, y, and z, and they are the one going essentially. These are the two going to have a higher up in the energy, and the rest of them, the rest of these three, which is they are in between, right? XY, XZ, and YZ, and XY. Those are the three that are going to take lower energies in the octahedral energy splitting from the original 5d orbitals. The question is, how much of the energy gap? So this is essentially, this is an energy splitting, and the question is, what is the gap between this? Is it the gap is going to be big, or is going to be small? So depending on your neighbors, the gap can be small, that gap can be big, and that the answer can be found from your neighbors. Okay, so that's what is called the strong ligand and the weak ligand. And the strong ligand is the famous strong ligand is the one with a lot of electrons, the Cn minus, and the weak ligand is something more like a neutral. And this is funny. This is what when they say that's mean the weakest one. Okay, water. If you remember, the water looks like that with the lone pair electrons, and those lone pair electrons can form the ligand coordination complex with the central atoms, where the Cn is a Cn with triple bond like that, with a negative charge, and this negative charge is actually located more focused onto the carbon side. So the carbon side is the one that making a coordination. Overall charge is negative, and the formal charge of carbon is a negative over there, and there the strong complexes. So strong ligand complexes, the splitting is, for example, like this, and the weak ligand complexes, the splitting is more like that, okay, in terms of energy field. So the energy splitting, relatively speaking, they are different. So this is essential magnetic properties and how actually they are going to be the one, and this is a splitting of the ion, and as you can see here, and you have the most important one is you have 5 electrons, okay, and the case for I am going to write it here, FeCN6 hexacyano ion complex 3 minus. You are going to need 5 orbitals, right? Which is a 3d5. So where you're going to put it in versus the one that on the left. Let me put a little distinction here. Right, so this is a weak field, and so therefore in this case is Fe aqua hexa aqua with 3 plus. Once again, this is the same Fe3 plus, Fe3 plus, 3d5. So 5 electrons, 1, 2, 3, 4, 5. And then when you have the energy gap is such a big, you're going to put 1, 2, 3, and you have an option that are you going to put this one up or are you going to put this one down, right? When the energy gap is too big and this one make it high energy situation, so their choice is, oh no, I'm not going to go up. I will go and choose myself in the one in the lower energy state. So therefore, FeCN6 is the one that is going to choose 5 d5 electrons, 3d5 electrons in this way. So ended up resulting only 1 unpaired electron. Whereas this one, okay, you put 1, 2, 3, and instead of putting the one in the by pairing up, you actually they would like to go to a little higher energy because the energy gaps, the octahedral splitting is so small. So then they can have this. So therefore, this one has 5 unpaired electrons, right? 5 unpaired electron spin. And so this, and both are paramagnetic. As you can see, this gives you a paramagnetic. That will give a paramagnetic. But which is much more stronger paramagnetic? The one with this one, right? So the spinning. So predict the number of unpaired electrons in each. Unpaired electron on this side is 1 unpaired electrons. And this one is 5 unpaired electrons. Okay. And then this is a diagram to show. So therefore, the relative large value for this energy splitting, they call this one as a delta. Okay. So see the delta here. So this small delta, a large delta, we can have a case low spin. So this one is essentially low spin. This one is high spin. And because of the split of these energies. Okay, that will be end of the essentially understanding this delta energy splitting and the octahedral energy split, and look for your lecture note in this section. Just looks like that.